Good day and welcome back for the third part of our discussion on integration by parts. To start off this video, we have the following indefinite integral. And instead of me just working through the details and explaining, I think this is a perfect scenario for you all to pause the video and spend a few minutes working through the example. So pause the video, give yourself 5 or 6 minutes. Note the hint here. You might have to apply integration by parts more than once. Let's see if we can evaluate. Hopefully at this point you've paused your video, you've thought a bit about the problem. Let me give you a quick integration by parts reminder so there's no confusion. When it comes to integrating u dv, we can write this as uv minus the integral of v du. This is the formula we think of as representing integration by parts. When we are using this formula, we have to make a choice of what's going to play the role for u, what's going to play the role for dv. And when it's possible, it's not always, it's nice to have u be a polynomial. So let's try that out. The reason I suggest this is a nice option is that when you differentiate u, it becomes simpler. And in our case, if dv is sine of 10x, v is going to be minus 1/10 cosine of 10x. And just to make sure there's no confusion, let me just note the following general antiderivative formula. If you wanted to antidifferentiate sine of kx, where k is any non-zero constant, if k is 1, an antiderivative of sine of x is simply minus cosine. But if k is something other than 1, if you used a substitution, you get back minus 1 over k cosine of kx, which one could easily check via a differentiation. So putting this to work for us, integration by parts, uv minus the integral of v du. We have that our integral is equal to minus 1/10 x squared cosine of 10x minus the integral of v du. So I'm going to go ahead and pull the minus 1/10 times 2 in front of this. So minus 1/5 x cosine of 10x. And once again, just to make sure there's no confusion whatsoever, the 1/5 is coming from 2 multiplied by 1/10. And because we also have this minus, I'm going to turn that into a plus because it's minus a minus. Now note, when we apply integration by parts, that doesn't immediately solve the integral for us. Instead, it expresses the integral in terms of hopefully an easier to evaluate integral. And in this case, we're going to need to use another integration by parts. And just note, as we've seen before, it is perfectly reasonable to involve multiple techniques of integration in a given problem, i.e. integration by parts and then a substitution. It's also perfectly reasonable to have more than one integration by parts. So in this case, doing a second integration by parts, I'm going to choose u to be x and dv to be cosine of 10x. And note, similar to a comment I've made previously, as long as we can clearly see where the integration by parts is being applied, you can keep using these names u and v. If you don't like to reuse that symbol, it's certainly fine to maybe say u2 and dv2. But if it's clear from your work and organization, as it should be if you're using good notation and organization, you're perfectly fine just using those same letters. So du is dx, and v is 1/10 sine of 10x. Which, if you're unsure about how we went from dv to v, you could, to the side, do a substitution problem, or you could double check this with a derivative. So applying integration by parts to this remaining integral. We have the first part, which we cut and paste. We rewrite it at each and every step. And then we have a plus 1/5, and I'm going to leave that out front just to make sure I'm very careful and distribute everything correctly. We would have uv, so x over 10 sine of 10x, minus the integral of v du. We'll pull that 1/10 out front, and what we're integrating is sine of 10x. And before I evaluate this integral, just to be careful and make sure I don't make any silly mistakes, I'm going to go ahead and distribute the 1/5 through. So just kind of cutting and pasting down one term at a time, distributing the 1/5. We would have x over 50 sine of 10x minus 1 over 50, the antiderivative of sine of 10x. Now we have a single remaining antiderivative, and note we've already antidifferentiated sine of 10x. It's minus 1/10 cosine 10x. So let's go ahead and substitute that in. The first two terms, once again, are just coming along for the ride. We do write them at each and every step. And then note we have a 1 over 50 and a negative sign out front. Then that needs to be multiplied by the antiderivative of sine of 10x. So a minus 1/10 cosine 10x. So minus a minus makes it a plus, and multiplying the 50 in the denominator by a 10 makes it 500. Which completes our example. So the reminder, it is perfectly reasonable to combine together multiple techniques of integration, which could even include more than one integration by parts. I'd like to finish up with another common example that involves a technique we have not yet encountered. So we're going to apply integration by parts to evaluate this integral of e to the x times sine of x. When we use integration by parts, we need to come up with an initial choice for u and dv. The general rule of thumb being whatever we choose for dv needs to be something we can anti-differentiate, and u, we are happy if it becomes simpler when we differentiate. In this case, we can anti-differentiate both functions, and neither of them really becomes simpler when you differentiate. So either choice would work perfectly fine. I'm going to let u be e to the x and dv be sine of x. This forces v to be minus cosine and du to be e to the x. And integration by parts tells us that the original integral, say from e to the x sine of x, is equal to uv, so minus e to the x cosine x, minus the integral of v du. And I'm going to take the minus sign with the v and go ahead and pull that in front of the integral. So similar to what we've seen before, this minus sign inside the integral turns the minus sign outside the integral into a positive, and then we'll have e to the x cosine x. And recall, with integration by parts, it does not solve the integral for us. It instead writes it in terms of another integral that is hopefully simpler for us to evaluate. And I say hopefully because in this case you would know this is no easier to evaluate than the original one. So what should we do? We don't give up in frustration or go look in our textbook. No, we apply integration by parts a second time. So if we apply integration by parts a second time, we need to again make this choice for u and dv. In this first application of integration by parts, I know that we could choose either function to play the role of u or dv. It turns out that whatever choice we make the first time, we need to remain consistent our second time. For example, if I was to choose dv as e to the x and u as cosine, that would be perfectly acceptable. It would just undo our work and bring us back immediately to this starting point. So what we want to do is continue progressing in this problem, so we're going to remain consistent with our choice. We're going to let u be e to the x and dv be cosine. So v is sine, an antiderivative of cosine, and du is e to the x. So just kind of cutting and pasting down, we have minus e to the x cosine x plus an integration by parts tells us uv, so e to the x sine x, minus the integral of v du. So what should we do next? Do we need to use another integration by parts? And it turns out the answer is no. Our goal, what we started with, is to evaluate this integral of e to the x sine x. And we've expressed it in this form. So this second line is equal to the indefinite integral of e to the x sine x. And note, the quantity we are trying to solve for appears on the other side of the equation. So we can now simply use a bit of algebra to solve for that desired quantity. Note, if I told you I is equal to a plus b minus I and asked you to solve for I, you would add I to both sides and you would divide by 2. Well, we can do the exact same thing here, where playing the role for I is this integral of interest. So if we add this integral of e to the x sine x to both sides, we're left with 2 of them on the left, and on the right we have the 2 terms involving the exponential, e to the x sine x and minus e to the x cosine x. And if we divide both sides by 2, we now have the desired antiderivative. But before I go any further, what am I missing? All indefinite integrals need a plus c involved. And this shows us a slightly different integration technique than we've seen previously. In this case, the integral that we are trying to evaluate is expressed again on the other side of the equation, and we're able to algebraically equate those together to evaluate the desired integral. Note there's nothing special about e to the x sine x. This just as easily could have been something like, say, e to the x cosine x. And this leaves us in a very nice position to just kind of summarize some of the key facts we've seen related to integration by parts. So integration by parts, we have this formula. The integral of u dv is uv minus the integral of v du. And in order to get started with our integration by parts, we need to make a choice. Which function in our integrand is going to play the role of u? And there is a mnemonic tool that we can use to assist us. So what we want to remember when it comes to determining u is liate. And what liate stands for is as follows. The L is standing for logarithms. The I is standing for inverse functions, so things like arctangent or natural logs. A is standing for algebraic functions. And algebraic functions for us, that really is a fancy way of just saying polynomials. T is trig functions. and E is exponentials. And how we use this mnemonic tool is that we want to choose our U value to be as high as possible on this list. Furthermore, another observation that we've made multiple times to just keep in mind is that dv must be something we can integrate. If not, we can't use integration by parts. And it's ideal if du is simpler than u. Also, let's finish up by just noting what types of integrals integration by parts is well suited to handle. So it works extremely well with things like x to a power, or really any polynomial, times an exponential. And it's also something good to keep in mind when you have x to a power times a function. There's never any guarantee that integration by parts will work in this scenario, but it's certainly an option that's worth considering. It works well when you have x to a power times a cosine or a sine. And we've also seen that it works really well for an exponential times a trig function, like sine or cosine. And integration by parts works really well with integrating inverse functions. So that is to say, if you were asked to integrate something like arc cosine, or maybe something like the natural log of x plus 1, integration by parts can be applied to evaluate both of those integrals. And this finishes up our current discussion. And we've really covered all of the material related to integration by parts, and what remains is just practicing. And integration in particular, which is our topic of interest for the foreseeable future, is something that really takes quite a bit of practice. So I strongly encourage you to make sure you're practicing suggested problems. Reach out to me when you have questions, and we will continue this on in our next video. So stay tuned and take care.